So here we are, our last but not least talk.
We'll see.
So Kalimat from École Polytechnique Fédérale de Lausanne. He's a PhD student.
Yeah.
Okay.
Yeah.
I was okay, and he will talk about how to compress signals in combining discrete Morse theory and other weird animals.
That's right. Thank you for the introduction. I want to thank the organisers. It's been a really lovely conference, all the speakers. I feel like I've really got something out of all the talks, and it's been nice having kind of a smaller thing where we can really like talk to each other. So it's been great. So, as in the introduction, I'm going to talk about signal compression reconstruction chain complexes using discrete Morse theory. And before I talk about anything, I obviously want to thank my wonderful collaborators here. I've got Celia and Stefania. This is kind of the EPFL DMT crew that I've been working with for the last 2 years, and they've just graduated. Should also take a moment to thank our supervisor, combined supervisor. Also, just before I start the talk, I know we're on a bit of a tight schedule, so if we start approaching kind of the end of my time, it'd be awesome if someone could tell me so no one misses the taxi or train. So, to start with, I just want to kind of situate the three main themes of this work in this Venn diagram. On one side, we're kind of trying to combine these ideas from geometry, kind of Hodge theory and Laplacian, with these more kind of like malleable ideas of homotopy, kind of deformation of tracks and the things that come out of discrete Morse theory. And we're kind of going to do this in the setting of some really kind of central machine learning ideas of reconstruction error. And Pavel was talking about fetishes earlier. I feel like the fetish of this work is this kind of central object of the chain complex. And really, you know, all these three worlds can kind of collide all within this setting. And because we're working in a machine learning setting, we need kind of finite dimensional chain complexes. Everything's going to be over R, so everything's going to be So what do I mean when I say a cellular signal in the applied setting? People use this word signal. Really, coming from algebraic topology, we should just think of these as kind of co-chains. So these are the kind of data points that we're working with. And if you haven't seen this before, I'm sure most of you have, you can really just think of the most basic example when we have a CW complex. A cochain is somehow a function on the n cells and n cochains. The n cells assigning each cell a real number. Right? So here, just think of function on the edges in the core. And these arise in lots of different settings. For example, when we have triangular meshes, people who do finite element and stuff work with this kind of like cochain data. And you know, we can assemble all these cochains of different dimensions into a cochain complex or dually kind of chain complex. And these boundary operators kind of keep track of how all the different dimensional cells and functions on them are glued together. And in some sense, give us kind of algebraic way to look at this structure. And so recently, people have started looking at the kind of machine learning pipelines that work with cochains. But here, instead of having just a single real number over each cell, we have kind of a vector over each cell. Right? And the way I like to think about these is what we're kind of doing in these kind of cellular neural networks is we're kind of trying to learn vector representations of each cell in a way that is kind of processed by multi-layer perceptrons, but take into account the kind of connectivity and the topology of the underlying cell. So primarily, people are trying to do the same kind of things that we do with images, except with these kind of cochain data as representations of cells and joining them together in specific ways that we can. So one of the key things in convolutional neural networks is what's called a pooling layer, right? So simply, if we have an image with these pixels, a pooling layer is a kind of way to kind of quotient together bigger neighborhoods, small ones. And the kind of heuristic for why people do this is to, as you go further and further down the pooling thing, your features look more and more global, or like more and more unique. So there's two kind of things happening here. At one level, we're compressing kind of the space of pixels, we're kind of quotienting things together. But we also have some sort of strategy to how we move the pixel values down onto the kind of quotient. And when we move into the world of these kind of cochain complexes or chain complexes, you need to kind of do two things. One, you need a way of kind of deciding how you're going to compress down the space or the whole cochain complex in general. But also a way of assigning, of moving specific cochains or kind of colorings on the edges down to specific cochains in the whole spaces. So there's two things. We're compressing the space, but also the kind of points or cochains in the space. So the first kind of question is, what are the right kind of maps to do this operation? And from our perspective, this is a choice, is that we propose that deformation maps are kind of good maps to do this, right? So our deformation attractive chain complexes, or kind of you can dualize this to cochain complexes, consists of generally a bigger space, C, and a smaller cochain complex, D. And we've got the cochain and chain maps between them. And the way we can think of this condition here is that we have this kind of injective mapping of D back into the large complex, but also that these guys are kind of chain or cochain topics. And what's nice about this kind of type of map is that it preserves the cohomology, right? If we're working with this cochain data, we assume that this is kind of a basic thing that we want preserved when we're doing our kind of correlation. Degree-wise, from the linear algebra perspective, these kind of look like projection maps onto a subspace in each dimension. And we're reducing the kind of dimensionality of the problem, much like the way that the kind of dimensionality is being reduced by pooling layers and convolutional networks. Now, generally or historically, looking at deformation tracks when people are trying to compute things like homology and homology, these are kind of aspects or properties of the whole space. So historically, you would say that deformation retract is good if it reduces the dimensionality a lot. But here we have kind of extra thing. We have the cochains, or specific cochains that are kind of like the data points in our space. So the question of evaluating which deformation retracts is good is slightly more a richer question. And this is where we start to kind of borrow terms from machine learning. And I think Bastian talked about this in his talk. This concept of reconstruction error and building codes, right? So if we have some sort of metric on space, usually kind of a vector space with point values, the idea is that we want to learn a kind of lower dimensional or latent space that kind of represents some of the main characteristics of the data. And what we do is we kind of pick a dimension of this space, we map the point cloud down and back up, and we compare the reconstruction with the original, right? And we use that as a way to evaluate whether we've learned a good kind of embedding encoding data. So if you make these maps with orthogonal projections, you kind of recover PCM. If you make them multilayer perceptrons, you get autoencoders. And if you kind of tinker around with the loss function and put things about the kind of persistence diagram of the points, you get some of the work that Bastian was talking about, with these kind of topological autoencoders. And the kind of simple or like basic idea is that we want to do this, but in the category of chain or cochain complexes, right? So we have this kind of, we want to use this concept of reconstruction error for kind of trying to compress the complex and the cochains at the same time. And what you need here is some sort of like norm, inner product, or even just a distance on these kind of cochain complex spaces, and you can kind of define this guy straight away. Now, what's really nice about using deformation tracks is that this kind of formula for reconstruction error from the machine learning world, you can really equate with this formula that relates the kind of homotopy that's doing the deformation retraction. So in this sense, and the key point of the work and throughout the talk is that understanding this kind of reconstruction error, how much the original thing is different from the reconstruction thing, it's helpful to actually have these explicit homotopies and work with that, right? So understanding the homotopies is really helpful for understanding the kind of reconstruction error.
So,
yep.
I'm a bit confused. If what you showed before is a definition of reconstruction error? Or
yeah, so this one is we're defining the reconstruction error of a specific cochain S, given these maps down and up.
So those are the maps in the contraction.
Yeah, that's right. Yeah, so here would be my phi and then my psi.
But that is a theorem.
So that's if they're deformation retracts, you have this equality.
Oh yeah,
yeah.
So yeah, thank you.
Yeah, so that's like an important point, is that we made the choice that we're only looking at deformation retracts. And given that, then we have this kind of equality. Does that?
Yeah.
All right, so the key questions given this setting is how can we find good deformation retracts that minimize this reconstruction? And further than that, are there parts of cochains or parts of these signals that are well reconstructed by certain types of deformation retracts and poorly reconstructed? So if you're coming from the pure world, maybe the kind of question of how to generate deformation tracks is if you just look at that definition, it's not immediately clear how you would efficiently find these deformation tracks. space. And this is where discrete Morse theory really comes into play. So discrete Morse theory is kind of a nice combinatorial way to quickly generate definition traces. Now, quick crash course on discrete Morse theory. Discrete Morse theory, I think, really comes from this idea of simple homotopy collapse, introduced by Whitehead. And the idea is that we're going to kind of pair codimension 1 cells together and deform the low dimensional cell through the higher one to kind of reduce the kind of cell decomposition of the space. Now, what Foreman did in 1998 is essentially to take these kind of like collections of simple homotopies, and if you arrange them in a certain way, you get things that kind of look like these combinatorial vector fields, right? And in a lot of ways, this functions in a similar way to Morse theory, right? You have these gradient flow paths, you have cells that are not paired by anything that become critical cells, and the dimension of the cells kind of act like the index of critical cells in Morse theory, right? And the key thing is that you can really do a lot of reductions of the CW complexation structure, reduce a lot of cells in an efficient and very combinatorial looking way. So our data really is something algebraic, right? It's these real valued cochains. Discrete Morse theory classically is really used at this kind of topological level, CW complexes, and you run into these problems of torsions. We can really skip all of that stuff and just focus on kind of variant of discrete Morse theory that exists purely at the chain or cochain. Introduced by Skolberg in 2005 called algebraic Morse theory. And this is for a kind of a thing called a basic cochain complex, which I'll define in a moment. But the consequences of moving to this algebraic level is that it's far easier to generate matchings. We don't run into problems of torsion and things like that. We can do everything with linear algebra, right? So we really have these kind of like nice algorithms to generate these things. And it allows us to liberate the definition of what's a cell and what isn't, and make some connections with other things that exist at the cochain. So what is a base chain complex? And I don't want you to think of base as like base point. Think of base as close as something like basis. So in discrete Morse theory, the cell structure is really important. The cells are the things that we're pairing. In the algebraic discrete Morse theory, the kind of algebraic version of a cell is just specifying a kind of direct sum decomposition of each chains. Right? So elements of this kind of direct sum and are now our kind of cells, right? They're kind of these subspaces of cells. And you know, the obvious or most simple example is looking at the standard basis of superficial cellular cochains. But something like this also works for things like cellular sheaves, where the kind of vector space sitting above each cell is now this kind of algebraic cell in this base chain. And what we need to do is kind of have a nice combinatorial structure that's going to allow us to do this kind of paring things down and choosing how to squash things. Right, so I'm sure you guys have seen something like this before, the kind of Hasse diagram of a CW or superficial complex. Right? Here, our kind of points represent simplices, for example, here, the 2 simplex. And these kind of adjacencies these arrows kind of represent adjacencies. So we can build the same thing for these completely algebraic base chain complexes, where our vertices kind of correspond to direct sum ends. And we have directed edges when the kind of boundary operator or co-boundary operator between these direct sum ends is non-zero. Right? It's kind of like algebraic adjacency. And these things you can kind of like build in fairly simply and store efficiently. And making a kind of Morse matching is kind of goes exactly the same way as you would imagine a standard discrete Morse theory, right? So what does it mean to match two cells? We're kind of picking an arrow, right? Picking an adjacency to kind of convert it. In the interest of time, maybe not going too much into the specifics of these conditions. We're really just trying to make this kind of like acyclic vector fields that you see in discrete Morse theory in Hasse diagram. And the condition of being able to kind of effectively have a nice connection or a nice adjacency turns out to just be a kind of isomorphism restriction of this boundary. And the story is exactly the same, but all at this algebraic level, right? So in the kind of topological world, what happens is that we compress a CW complex or a superficial complex down onto a superficial complex, and it's just kind of critical cells. The same thing happens here, is that we get kind of chain complex, cochain complex that's just critical cells. But our input is really any base chain complex. Okay? And we get this kind of like nice net motion. So the nice thing about working with this theorem and with discrete Morse. Yeah.
In the limited chain complex, the summands have to be one-dimensional by definition or not?
No, that's the nice thing about this algebraic discrete Morse theory. The summands can be n-dimensional. So when we work with something like a cellular sheave, the over each cell is like usually something that's maybe high-dimensional, right? And that's in the simplicial neural networks, you need like theory to be able to deal with that. But when you go to collapse something, you need to have an isomorphism between their spaces. So cells that you collapse have to at least have the same dimensional space over them.
Okay,
does that make sense? Yeah, that was one of the main reasons for moving to this algebraic thing, so that we could have bigger kind of vector spaces sitting over each cell. And what's really nice about these theorems in discrete Morse theory is that you have, once you choose your matching, which is not a difficult thing to do, right? Or it's not as difficult as maybe finding a definition of colorways, you have a formula for computing the boundary operator of this, or the co-boundary operator, and computing everything. Also have formula for these maps that kind of play the role of an encoder and decoder. And you have a formula for the homotopy that is somehow related to this reconstruction error that's really helpful for proving things. Right? So having explicit formula that we can throw in this algorithm and generate is something really nice, I think, about this discrete Morse theory perspective. So far, we've really looked at this kind of homotopy stuff, how we're compressing things and expanding it, and how we're trying to evaluate with this machine learning stuff, reconstruction error, these notions of autoencoder. The final kind of key ingredient is these notions of geometry, right? Like what are these code chains? How do they reflect somehow the geometry of the space? And the kind of secret sauce of adding geometry to these code chain models is giving an inner product to these code chain processes. And what these give you is first a metric on the code chain, right? So we have a way of evaluating a code chain reconstruction. But maybe surprisingly important the first time you see it is that we have adjoint maps. And the adjoint maps of these inner product spaces allow us to define this kind of combinatorial analog of little passing. Right? So for me, the first time I saw this, I found it to be a really strange formula. Right? What we do is we start at Cn, we go down, we go up, and we go up, and we go down, and we add it all together. Right? So if you come from TDA, persistent homology, this is something that looks pretty bizarre because you're doing something kind of covariant and contravariant, adding everything together. Right? And this is something that's not functorial, right? So if we have like filtered spaces, these kernels aren't going to map to each other. Nevertheless, you have some amazing facts about this operator. It tells you a lot about the geometry and topology of the space. Right, so simply, just looking at the kernel of this guy, we recover the homology or homology of the space, less the torsion part. Which I think is kind of an amazing fact, right? You're doing this weird operator, why should I do it? And the proof that Ekman did in the 1940s, really just a couple of lines of homology. Secondly, we get a nice way to decompose code chains into meaningful components. Right? This is called Hodge decomposition. And it splits code chains orthogonally into this kind of homological or cohomology part, and this kind of co-boundary operator or boundary operator part. And if you're working in physics, for example, looking at one code chain, which you can kind of think of as one forms, this splits kind of one forms into like a cohomological part, a gradient-like part, and a rotation. So this Hodge decomposition, depending on the application, actually has quite a lot of interpretation. And finally, the eigenvectors of this guy can really be thought of as a generalization of the eigenvectors of the normal velocity. Right? So in some sense, these are like Fourier basis for cochains in any dimension.
This is the combinatorial counterpart of the classical Hodge decomposition.
Exactly. Yeah, exactly. Yeah, absolutely. And the nice thing is that in these finite dimensional things, this is like stuff that you can really compute, you can really work with. Yeah, but this is, the finite dimensional version of the story is like much the same. And, importantly, these eigenvectors, you can think about eigenvalues, their frequency in a similar way. And these eigenvectors kind of sit nicely in this Hodge decomposition. You have different types of eigenvectors. You have cohomological ones, your kind of gradient or co-boundary-like. So on the face of it, there doesn't look to be much connection between these more geometric ideas of Hodge theory and these more kind of combinatorial ideas. But to me, at least, this is more of an observation, is that they both kind of feature an element of partial matching of things, right? So the way that you get these kind of eigenvectors is by looking at the singular value decomposition, right? And just looking at our boundary operator here, what happens in the singular value decomposition is that by looking at the eigenbases here, this matrix with respect to the eigenbases here, we get a matrix whose only has entries in the diagonal. Right? So in some sense, these entries are pairing eigenvectors in dimension n and dimension n plus 1. So now we have this more kind of liberal definition of what a cell can be. When you plug in the kind of Laplacian eigenvectors as your cells, what happens is that it does this kind of nice straightening out of the Hasse diagram of the adjacency relations of the cosine complex, where here now instead of being the cells, we've got the eigenvectors and we're kind of matched with each other in some nice way. And just more of an observation is that throwing this in the DMG machinery, you get a nice kind of deformation retract onto this harmonic space, right? So in some sense, this kind of notion of pairing is inherent in both of them, I think, one of the ways in which they're connected, at least algebraically.
It should be obvious, but I'm having trouble seeing why you get the only entries in the diagonal.
Yeah, so this is it's the existence of an inner product gives you this kind of singular value decomposition of the matrix. And the theorem of the singular value decomposition of these matrices is that you have only entries in the diagonal.
So it seems like you're saying that you have an eigenbasis for all the cochains, right?
Yeah, because so this Laplacian is self-adjoint.
Yeah.
So you have the eigenbasis.
Right.
And in some sense, right, that's what the SVD is doing. Like it's kind of following from the self-adjointedness. It pairs the eigenvectors into.
I would believe that if it was the full Laplacian, right, going from Cn plus 1 to Cn plus 1, then obviously you have the diagonal. But you're only seeing this delta n plus 1, which is just part of the Laplacian.
Yeah, but okay, so right, if you take the SVD of this, right, SVD of this, they're kind of related, right? Like these guys. The eigenvectors of this guy, right, will be the same as the right singular vectors of this guy.
Okay. I see a path from here.
Yeah. But yeah, I think, yeah, somehow this SVD is a way of pairing the eigenvectors of this operator on both sides. Okay. And I'll show you a picture geometrically of what's happening. Here, I'm not sure if you guys have seen the graph Laplacian before, it's eigenvectors, but here I've got kind of a graph of a single-cell experiment. And what I've tried to do is draw a zero eigenvector in the coloring of the nodes. Right? So imagine this is one of these eigenvectors, and it's colored the nodes in a certain way. And on top of that, on the edges, I'm drawing an eigenvector of the one Laplacian, right, which is coloring of the edges. And these guys are paired by the co-boundary operator. So this is kind of like the gradient of the color on the nodes gives us the color of the edges, right? So these two eigenvectors are in some sense paired in this particular way. Right? I don't know if you can see it clearly from the picture, but you know, as the color changes, you can see the edge weight increasing, right? Just the change of color. Right? So there is some sort of like geometric way to see this kind of pairing of these different eigenvectors in different dimensions. All right, so far we've really just gone through background stuff. I want to talk a little bit on what we actually do in the paper. And one of the main questions is that, you know, if we're only generating deformation tracks in this way, which deformation tracks can we actually get from Morse matchings, right? So if I have these kind of topological cells here, there's no real way you can kind of draw an arrow in where the Morse deformational tract gives you the deformational tract you're getting in this section. So to kind of say what deformation tracks are possible, we need this kind of like, I think, sensible notion of equivalence. Right? And then we say two deformation tracks are equivalents. Equivalent if we have this kind of like isomorphisms fitting into the community of these different encoders and decoders. And importantly, under this notion of equivalence, when we have kind of equivalent deformation tracks emanating from the same complex, we have the same reconstruction. So the thing we're trying to study is kind of invariant. And what's nice is that if you give me a deformation retract, right, without specifying what the base is, the way that the cell decomposition is, I can give you a cell decomposition and a matching of that, right, kind of like algebraic cell decomposition, such that I recover that deformation retract. So in some way, all deformation retracts of chain complexes can be recovered as Morse matching with the choice of appropriate bases. And the kind of philosophical reason that that's important is that understanding deformation retracts in general is kind of equivalent to understanding Morse retracts. If we prove something about these specific kind of retracts, then that applies to all deformation retracts because they're equivalent in this form. And it gives us explicit nice homotopies, and it helps us to understand and prove things about reconstruction error in general. So one of the main questions is, now that we have this way to break down signals into different components that have different physical meanings, are there kind of types of deformation retracts that are good at encoding the different parts of these signals? And it turns out the way to think about this is not what the deformation retract does compress, but it's kind of the absence of compressing certain codimensional cells that leads to the right method. So we call a Morse matching n-1 free if no kind of n cells paired with n-1 cells. So here, just simply, I haven't paired any 1 cells with any 0 cells. And it turns out that, you know, this is exactly, kind of in an if and only way, the kind of thing that preserves specific parts of the Hodge decomposition, right? So if I have any signal, right, the reconstruction error is going to be essentially 0 on these two parts of the Hodge decomposition, if and only if I have an empty times. So it gives us a really simple criteria for the kind of deformation retracts that we want to use, given we want to preserve some particles. And this works given any base or any way that you decompose the complex. It's really just a matching between these two dimensions that you need to avoid. And you can kind of take the adjoint of this theorem and get the kind of other side of the Hodge decomposition, if that's what you're interested in. And here you use co-chain maps rather than chain maps. And one of the intuitive ways to think about this is that when we're reconstructing the signal, it just moves everything onto the critical cells, right? This kind of subcomplex of critical cells lying in the biggest space ends up being the way that we reduce the complex. So I want to spend a little bit of time going through this example. Right? Here I've got kind of one co-chain or function elements. And when I kind of do this kind of 0-1 free matching, I'm not matching any 1 cells with any 0 cells. It moves the signal along here through deformation down onto this kind of like this part here. Right? And we reconstruct it, and suddenly the signal's been removed from these areas. And what you can see is that even though the signal lies on a lower dimensional space, this lower dimensional subcomplex of just critical cells, from the lens of this part of the Hodge decomposition, right? This is the projection of the eigenvectors, these type of eigenvectors before and after. Nothing has changed. Right? So in some sense, we've successfully reduced the dimensionality of this co-chain or chain complex that we're working with, without altering some characteristics in some part of the Hodge decomposition. And the philosophy for me is that in some sense, this is like a measure of having encoded these parts in the Hodge decomposition in the lower dimensional chain complex. So in practice, how do you kind of find these guys? Right? The goal is kind of trying to find these discrete Morse theory matchings that minimize reconstruction. And rather than trying to find heaps at once, we have to verify this kind of acyclicity conditions. What we try to do is really just locally find one. In some sense, you can really easily find the best pair that minimizes reconstruction at each step. So in some sense, this is kind of like a combinatorial gradient descent. Trying to find like one good pair each time, do my compression, and then find one pair. And what's nice about this algorithm is that you can prove that this is linear complexity in dimensional signal. If the complex is sparse, which most complexes like shapes and stuff that we worked with are sparse. And you can prove that because, in some sense, we've removed the torsion of the space by making everything algebraic, this guy converges to something else. Right? And essentially, what's happening is that you're losing one part of the Hodge decomposition, or at least the dimensionality of one part of the Hodge decomposition in doing this. Right, so let's look at a slightly bigger example. And this example, I always have to stress here that for some reason, the hardest part of this paper was getting Matplotlib to plot the colors in a kind of sensible way. I don't know if you guys have ever experienced that, but I find it extremely painful. So really note the scale here, right? The scale changes. So we start with some original kind of height function in the data. And what the algorithm is doing is kind of eating up these cells that have kind of low values, right? It's saying these guys aren't super important, observing things. And it moves those low values kind of to the middle band of the chain, right? Everything kind of gets aggregated up to the middle. And when you reconstruct it, not looking at the relative magnitude of these, most of the kind of cochain signal is now in the middle band, right? Rather than the top band. Right, so in some sense, these have a really different distribution of where the cochain is. But despite that, they still kind of look the same for the Hodge basis. Kind of like float this in such a way that this part of the Hodge basis is perfectly reconstructed. So I don't think anyone's tried this kind of thing before, at least in the literature that I've seen and tried to do this. So to kind of at least see that this algorithm of iteratively selecting things is working well, we compared with the baseline of just kind of like randomly selecting things. And as you can see, these kind of like optimal pairings have much lower loss than doing random things. So at the moment, we only really have a random baseline to compare this with and how it's doing, but I invite people to try to like approach problems like this because I think as people start to integrate more machine learning stuff into this, problems of kind of compressing these cell complexes will become more important. So yeah, paper's up on archive at the moment, and what's cool is that you can go and if you have any kind of cochain data like this or some visuals, cellular networks, you can this code's kind of like ready to go, mainly influenced by my colleagues. So in summary, what have we learned? On the theoretical level, there's this kind of nice connection between the SVD, these kind of like Laplacian eigenvectors, giving rise to this kind of canonical Morse matching that deforms onto the harmonic space. And any of these deformation retractions, if you give me one, I can find a Morse retraction that kind of recovers it. Right? So this space Morse retractions kind of covers all deformation retractions. In a practical sense, what we're kind of doing is sparsifying the complex in some way while retaining some sort of reconstruction error that's nice on the part of the Hodge decomposition that we care about. And on the algorithmic front, we know that this kind of sequential collapse algorithm converges in a predictable way, and it outperforms this kind of like first step of a random column space. So that's the end of my talk. Thank you.
Any questions?
Back to the slide where you showed the URL.
And so at the moment we were just using toy signals, really just these kind of alpha complexes of 2D point clouds, so we could really see what's going on. And more as a demonstration that the theorems are working. For us, that was the main part of this paper, was trying to set up the machinery. But in the future, what we're working on at the moment is trying to integrate this into these kind of simplicial or graph neural networks. Graph neural networks or simplicial neural networks, where you're reducing these like high dimensional vector representations. So any of the benchmarks of that is kind of what we're targeting to see if these pooling layers help have this kind of longer or bigger global structures at the end of these pooling layers in the same way that works for the convolutional networks.
So very nice talk.
Thank you.
I heard it before, so. I have a question. So, like the essential input for Hodge decomposition is the scalar product on these chain levels. Like you are choosing, you take transpose. That means that you are your scalar product. You assume that all the simplices are orthogonal to each other and the length one.
Yeah. So in this, we do it for any scalar product.
Right, exactly. So you take the standard assumption. So simplices are orthogonal to each other and the length is one. Now, in geometry, like we have these complexes, and when we sort of think about these meshes, etc., right? I don't think that this assumption that all the simplices are orthogonal to each other are the right assumption, right? So that typically this Hodge decomposition have played an important role, like for Chigurh's inequality work, where he used the scalar product of these manifolds, and they were definitely not this type. So have you explored different scalar product as an initial?
Yeah, so the theory is built to, the reconstruction theorems and stuff like that, they're built to accommodate any scalar product, right? Most of the theory is. The thing you lose, interestingly, is that when you come back, you're not only on the critical cells. That's the main thing you lose when you don't have orthogonal based elements. Yeah. But all the other theorems still work. And yeah, I have actually spent a really long time looking at what kind of scalar products work for a Vittoris-Rips complex, right? There's actually not a lot of good theory. Or I mean, I think there's some things that are, yeah, it's like, at least in a triangular mesh, you can compare it with the scalar product on the manifold and find scalar products, as you say, that converge to that. What is the Vittoris-Rips complex in a product converging to, right? And there's some work by Smale about Hodge theory for metric spaces. I think that it's probably like the best answer to that, when you do Hodge theory just on general metric spaces, and they have nice inner products that are defined there that I think are probably the answer to that question, that generalize in some sense what people do with graph Laplacians and diffusion stuff. So, but yeah, the inner product thing is really non-trivial, and there's not heaps of. It's actually quite hard to find good inner products for non-manifold simplicial complexes. That's a good question.
I don't know, I don't have a question, but when you mentioned this, like the analogy with the Fourier coefficients and this drawing there, I mean, I was thinking about this, the interpretation of Fourier coefficients as waves. And so it would be interesting that you can see some dynamical aspect of how things evolve on a graph reflected in your, your framework. I don't know how to.
I mean, this. Yeah, so there's, I can't remember who wrote the paper, but there's a paper called something along the lines of like dynamics on simplicial complexes or something, where you make the same kind of diffusion equation of like.
But so yes, so this is known that I mean when you see oscillations on a graph, then really this coefficients, the oscillations are based on the Laplacian number x, then the eigenvalues of Laplacian.
There's a differential equation where it's like du dt equals the Laplacian of u.
But what would be really exciting is that you see like a real data evolution reflected here, not like.
Yeah, so I mean, yeah, like the same thing works for like higher order cochains on simplicial complexes. You can make the same differential equation. You can do the diffusion. It diffuses to harmonics. Everything's kind of the same.
Yeah, but for example, like that, if you can measure the attention of a neural network working with your data, if this attention pattern during learning is going to concentrate on some Fourier modes, it would be like really amazing.
Yeah, absolutely. I think that, yeah, there's probably, especially in these graphical networks and the simplicial ones, the Laplacian really is a central thing for kind of convolving neighborhoods together and their vector representations. So it, in some sense, yeah, it's kind of limiting towards trying to make things more and more harmonic. But yeah, I think that it's still kind of early with these algorithms, and people haven't really got their heads around what is like cochain data that's really. What are the kind of benchmark tests for simplicial neural networks is still pretty open, I think. Like, where is the cochain data that we actually are going to analyze with these? That's, I think, still an open question. And how do I interpret this diffusion in those settings is still, I think, quite an open question.
Any other question? Thank you.
Thank you for beautiful talks for the speakers, and thank you poster speakers for presenting your work, and participants for coming. It was very nice to have you here, and see you soon.
Thank you for the